Welcome to the deep dive. Today, we're really getting into something foundational for aviation instruments, the gyroscope.
Absolutely.
And if you're gearing up for those air transport pilot license theory exams, well, this is definitely for you. We're aiming to boil down the key physics, how they work, and crucially, the errors and corrections that, always seem to pop up on those tests.
That's the plan, yeah. We're tackling the core concepts, rigidity, precession, that tricky business of wander, and breaking it all down into understandable chunks.
Good.
We've looked at materials covering into basics right up to the fancy new optical gyros. The goal here is simple. Give you the knowledge to confidently handle those ATPL questions on gyros.
Okay, let's start at square one then. Before we even think about an instrument panel, what is a gyroscope fundamentally?
Well, at its heart, it's just a spinning thing, right? A rapidly spinning rotor, usually a disc that's symmetrical and mounted so it can move freely.
Like a spinning top.
Yeah.
Or even the Earth itself.
Exactly. Those show gyroscopic properties. But for aircraft, we're talking about much smaller, highly engineered rotors, maybe, 2 to 5 centimeters across.
Tiny.
Tiny, but spinning incredibly fast. We're talking anywhere from maybe 4,000 RPM, which sounds fast, but is relatively slow for these, up to 55,000 RPM in the really precise ones.
Oh, wow. That speed must be key to the whole thing.
It's everything. And here's a really important point right off the bat. When we talk about the gyro's orientation, we mean the orientation of its spin axis, that imaginary line it spins around.
Not the disc itself, but the axis. Got it.
Right. And it's this super fast spinning around that axis that gives us the two magic properties we need for instruments, rigidity and precession.
Okay, rigidity and precession. Let's unpack those. Rigidity first. Pilots often call it stability or maybe stubbornness. What's the physics making it so stable?
Rigidity, yeah, or gyroscopic inertia. It's the tendency of that spinning axis to stay pointing in the exact same direction in space, unless, of course, you force it to move.
And that comes from basic physics.
Yeah.
Newton's laws.
Pure Newton. It's the inertia of all that mass spinning quickly. And importantly, these laws work everywhere, which is why we often say the gyro is fixed relative to inertial space.
Inertial space. That term comes up a lot. What does that mean practically for, someone flying an airplane?
It means the gyro's axis wants to point towards something incredibly distant, like a star, that isn't accelerating. So imagine a perfect gyro, no friction, nothing.
The dream scenario.
Right. That axis would just keep pointing at that star, completely ignoring the Earth spinning underneath it, or the plane banking and turning. It's trying to stay fixed in that non-accelerating reference frame. That idea is, well, fundamental to how inertial navigation works.
So the gyro wants to stay still in space. The challenge then is mounting it so the aircraft's movements don't mess that up. Which brings us to gimbals.
Exactly. Gimbals are the clever suspension system. They basically create joints, allowing the aircraft, which is attached to the outer part, to pitch, roll, and yaw without twisting the inner spinning gyro off its axis.
Okay, and we have different types. One gimbal versus two gimbal systems.
Yeah, and the difference is crucial. A one gimbal system gives you some freedom, usually in pitch and bank. But if the aircraft yaws, turns left or right, that movement does get transferred to the gyro. It runs at a give in that direction.
So limited use.
Right. Good for things like rate gyros, where you're measuring the rate of turn, not trying to hold a fixed direction.
But for holding a direction, like in a heading indicator or an artificial horizon, you need more freedom.
You need the full setup.
Yeah.
The two gimbal system. With two rings, an inner and an outer, the aircraft can pitch, roll, and yaw, and the gyro axis inside remains undisturbed, pointing steadily to space. That's essential for your primary DJI and artificial horizon.
Now, there's a point here about degrees of freedom that can trip people up in exams, especially with ESA.
Yes, good point. Some physics texts might call a one gimbal system a 2-degree of freedom system, counting the spin itself. But the ESA convention, the one you need for the exams, says, because you can't measure anything along the spin axis. You measure changes perpendicular to it. So,
all right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best